And what I'm going to do is just kind of emphasize, underscore, highlight the things I normally do. You guys ready? Okay. This slide, chapter 17, is a little bit challenging because the main thing that holds all these molecules together is that they're not soluble in water. That's it. Lipids, not water soluble. Saccharides, water soluble. Amino acids, proteins, they're water soluble and water loving. And they both saccharides, and you're going to see in chapter 18, amino acids have some real common features. There's some things you can hang your hat on and say, this is kind of what a saccharide looks like. It has a carbonyl, it has OHs. This is kind of what amino acids look like, and we'll see that in a few minutes. But lipids just cover all this stuff that is not water soluble. And what is that stuff? So this slide here kind of categorizes it for you. Saponifiable, that they can react with sodium hydroxide to form soap. Simple saponifiable lipids are triglycerides, and triglycerides have in them fatty acids. All right, that's the building block of the triglycerides. Complex lipids, saponifiable, complex phosphoglycerides. Now what you're going to see here, glycerides, phospho and triglycerides have glycerol as their link. And you're going to see some similarity. You should be able to detect some similarities between this and this. And these have fatty acids, 2 fatty acids. There's 2 fatty acids on here. There are 3 fatty acids on the triglycerides, hence plus a phosphate. That's phosphoglycerides. And then I'm going to point out the steroids and the sphingolipids. All right, so let me see. I wrote down my slide numbers that I want to look at. Slide number 3. I could just advance through them, but 6. All right, fatty acids. There's your building blocks. And those are 2 fatty acids. You should, I've got a little list. We'll get the light on later. Things you should draw or know from chapter 17. Structure of stearic acid, oleic acid. You got it right there. Stearic acid, oleic acid. Here's the acid. 18 carbons long, double bond in the middle of the oleic. Slide number 9. Now these should look familiar from last Monday. Fatty acids. Even when they have a double bond in them, it's cis. It's always a cis double bond. That's the naturally occurring bent in fatty acids in nature. Trans, I think it might be the next slide. You can see that with a cis double bond, you do get a kink in the molecule. It's got a kink. It's got an elbow in it, and it is right in the middle. There are 7 carbons over here. There's 7 carbons over there. That baby's right in the middle. And it gets you this kink in there. What happens if you look at here? I've got a double bond. You can't hardly see it. Comes in here, goes in one side of the double bond, out the other side of the double bond, and it doesn't really look any different than a saturated fatty acid. Except now it's got a double bond in there. It's got a different shape. And the shapes of these fatty acids, once you get them on the triglycerides, factor into how they form cell membranes. Number 12. Okay, and the key point here, what are we looking at here? Melting points of fatty acids as a function of whether they are saturated or unsaturated. I just showed you stearic acid, 18 carbons long. It melts at 70 degrees centigrade. All right? Oleic acid, 18 carbons long, about the same molecular weight, same size molecule. You would expect it to have a similar melting point, similar, nothing similar about it. You put a double bond in there, and it drops that melting point down to about 15 degrees centigrade. So it's dropping at 50 degrees. One double bond. This is the fatty acid that's in beef fat, lard, solid at room temperature. You take a spoon, you dip in there, and you get lard. Okay, or Crisco. They've made Crisco to be like lard, but it's a solid at room temperature. Comes from beef, which are warm-blooded animals. Here's oleic acid, comes from olives, olive oil. Linolenic, 3 double bonds, minus 10 degrees centigrade, comes from salmon, not warm-blooded, cold-blooded animal, swims around next to an iceberg out in the Pacific Ocean, minus 5 degrees centigrade. And what's the beauty of this? The triglycerides floating around in the salmon's bloodstream are liquids. Okay? That animal wouldn't be able to survive with this kind of a triglyceride. Triglycerides build off of stearic acid. Their blood wouldn't float in cold water. They would solidify, but you have like lumps of fat floating around in your bloodstream. Doesn't go through the heart very well. What you'll see, we're into biochemistry. We've already gotten chapter 16. We're dusting off chapter 17. Going to go into chapter 18 and then 20, 19 and 20. I don't think these things, I don't think it's an accident that salmon, we get omega-3 fatty acids from salmon, and that their triglycerides are polyunsaturated, low melting point triglycerides. I don't think that's something the salmon figured out. It's just my understanding of it, from my understanding of natural laws and how things work. There's a great deal of intelligence behind that kind of triglyceride float in the salmon. But here's what the effect of double bonds are on melting points. These are all 18 carbons long. They've all got about the same molecular weight, but dramatically different. So know what impact double bonds has on the melting point. It lowers the melting point. You don't really have to remember these numbers. You need to remember the direction things are going. Unsaturated fatty acids have a lower melting point than saturated ones. All right, a triglyceride. Here is, so you should kind of grasp what a triglyceride is. Here's the glycerol. That's where the glyceride name is coming from. It's got glycerol as its backbone, 3 fatty acids hanging off of it with ester linkages. So these aren't fatty acids anymore. They're ester bonded to the glycerol. Here is an example of this is how you would make one. If you had the glycerol plus 3 fatty acids, you'd form your triglyceride and 3 molecules of water, which is what your body can do. The proper enzymes, it can put together these triglycerides. And the very next slide, okay. This slide, just in a real basic drawing, is showing you the major components of a triglyceride. glycerol backbone, 3 fatty acids. And yeah, this is just showing you, here's olive oil. Here's your oleic acid in olive oil. It's not all oleic acid. It's got 2 other fatty acids in there. A little bit of stearic, a lot of oleic. Here is beef fat, a lot of stearic, and a little bit of oleic. So even beef fatty acids aren't entirely that. You can see it, that thing melts at 70 degrees centigrade. A mixture of these two probably would melt a little bit lower than that. The cow doesn't have to be that hot to keep that liquid. This slide just quickly shows you the 3 reactions that triglycerides can undergo. You can hydrolyze them back into the glycerol and the fatty acid, saponify them to form the salt here. This is why it is a saponifiable fatty acid. You can react it with sodium hydroxide and form soap. And then you can hydrogenate the double bonds in unsaturated fatty acids, hydrogenation. And the main reason they do that is to raise the melting point. You can actually turn olive oil into margarine if you hydrogenate it. You got olive oil that it's an oil, it flows, you hydrogenate it, goes up a little bit. Slide 26 and 29. 26. Okay. Now, a minute ago, you had the block kind of a rough draft of what a triglyceride looks like. If I covered that up, all of that, we're looking at a phosphoglyceride right now, all of that is common to the triglyceride. Glycerol backbone, 2 fatty acids. Instead of the 3rd fatty acid, you have a phosphate and an X group here. So my expectation is that you would be able to identify or at least draw this much of a triglyceride. All right, and then you got your 3 fatty acids coming off here. They're longer than this. Might have a double bond in there. This is your triglyceride. The phosphoglyceride is very similar. Fatty acids coming off here. All right? So to that point, the phosphoglyceride is the same, has all that in common with the triglyceride. Here's the difference. Now, we're going to come off of here and we're going to put an oxygen, and instead of that, this is a phosphate ester. We're going to put our phosphorus right there. And there's 4 oxygens attached to the phosphorus. Phosphate, remember, phosphate is PO4 with a -3 charge. Phosphoric acid is H3PO4. So we got a PO4 group right here. And then all I expect you to know, actually, yeah, off of this oxygen, there is something attached there. It can be choline, acetylcholine, different things. You change X, you got a different phosphoglyceride. There isn't any particular phosphoglyceride that I would ask you to draw. But I might say, draw the general structure. And I mean, even if you came off of here and just said there's a fatty acid, and then this kind of structure, be able to recognize a phosphoglyceride. This is a main component of cell membranes. In general, cell membranes. Okay. 26, 29. What did I want to show you on 29? Sphingolipids. All right, now you're not having a glycerol backbone. Here's your backbone. It's sphingosine. There is a fatty acid here, but it's bonded to the sphingosine with an amide bond, not a ester bond. And there's another non-polar group here, non-polar group here, and then you got this group here. So sphingolipids, you don't need to draw these, but do know that this is the main component of nerve cell membranes. So all the other cells in your body are using phosphoglycerides. Nerve cells, the myelin sheath, the cell membrane around your neurons and connectors of your nerve cells is sphingolipids. I got to erase that. Okay, now on your notes, I'm going to draw something here. I want you to draw it, and I want you to be able to draw it. Can I erase this? All right. We'll start out with something you're very, 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 very familiar with, whether you liked it or not. You're very familiar with this, a six-membered ring. Now start over on the left side of your notebook, because we're going to move off to the right here. So you got a six-membered ring. Somebody draw a six-membered ring. That far? Okay, now coming off of this six-membered ring, draw another six-membered ring. Okay, so now we got two fused six-membered rings. What do I mean by fused? These two carbons right here are in both of those rings. Okay? Now, see this upper corner right here? Upper right-hand corner, draw another six-membered ring. Coming off at that spot right there. Now we got three fused rings. Okay, this is the last one. Now it's not going to be a six-membered ring. Just draw a straight line right there and put a roof over top of it. Put yourself a five-membered ring right there. What is this? Steroid nucleus. All right? And if I ask you, draw the steroid nucleus, this is what I want to see. This is the basic foundational structure of the steroid molecules. And I don't know what slide that is. Yeah, here we go. All right, so that's what you just drew right there. And there's 4 carbons there, 5, 6, 7, 8, 9, 10. You see, so the another 4 carbons makes that ring, another 3 carbons makes that final ring there. That's your steroid nucleus. If you looked at carbons, so these 2 carbons are bridging between these 2 rings, fused. That's what we would refer to as fused rings. They are integrally attached to one another. They're not, and so this makes up the steroids. There's cholesterol. So cholesterol, right here, we would refer to that as the precursor. So this is the molecule that your body in a metabolic pathway would pull in cholesterol, make pregnenolone, progesterone. From the progesterone, you can make cortisol, testosterone, mineral corticoid, which has a lot to do with reabsorption of various ions in the kidneys. From the testosterone, you produce estradiol. So here's a female sexual hormone, and this is also a female hormone. And in between, there's the intermediate testosterone. So even in the female metabolic pathway, you are converting progesterone into testosterone into estradiol. And for the male, it's stopping there at the testosterone. So that's why females will have this and some of that. There's a certain amount of this that is appropriate because it's actually an intermediate to make estradiol. Right? And those are all steroids. And in the course I'm in right now, or the course I was in last fall in particular, I'm learning, and this time too, I'm learning the versatility of these steroids. They can pass through the cell membranes much more easily than lots of other molecules. They don't particularly need an active transport. And what do? Once they get through the cell membrane, they go and they act on the nucleus of the cell. These steroids then become potent effectors of one thing or another in the nucleus, triggering certain things to take place at the level of DNA or gene expression, etc. So you can see this steroid nucleus here, and there's different things. These molecules aren't dramatically different. Here's testosterone. I thought I had progesterone and testosterone on the same slide, and there's not a lot of difference. They're similar. And here's vitamin D3, and you don't see this exactly, but if you were to break that bond right there, okay, you can see how then you would have this little piece right here unravel, and so that is also a steroid. It's just unraveled a little bit. It's broken one bond right there. That's vitamin D3. Okay, what you should expect questions like, which of the following is a steroid? All right, out of chapter 17. I will have some multiple choice questions that say, which of the following is a steroid? Sphingolipids, phospholipid, testosterone, etc., etc. So you should be able to pick out a steroid from something that isn't a steroid. I won't say draw testosterone or estradiol. I don't expect you to nail these things down to that level, but to know, I will say this: draw the steroid nucleus. So I expect you to know what is the fundamental structure that is associated with steroids in general. All right, and then just finally, this shows you the complexity of a cell membrane. So here's the cell membrane. Here's inside the cell, outside the cell, hydrophilic environment. Everything's floating around in water in here. Water is the solvent, is the mobile phase. Water outside the cell. But what do you have here? In the middle, you have these nonpolar chains coming off of the phosphoglycerides, sticking down and sticking up. So you got a lipid bilayer. Here's a layer of phosphoglycerides. Here's a layer of phosphoglycerides. And what do you have right there? You've got a nonpolar barrier that doesn't let water or polar molecules pass through. These things, which are lipids, can kind of slice through this thing pretty easily and come through. Other things, like glucose, which is polar, has to be transported in and out of the cell. And there would be a protein here that would be a channel for glucose. Protein that might be a channel for sodium and potassium ions, calcium, magnesium ions. These are protein molecules embedded in there with specific tasks to get certain things in and out of the cell. It's an incredible structure, okay? Antibiotics, general antibiotics, are designed to attack the cell membranes of single-celled organisms. So you have a bacterial infection. You know that a virus, what do I call it?
Antibacterial. What are you looking for?
The prescription you get for antibiotics. Antibiotics don't do anything with the virus, but they attack bacteria. Bacteria is single-cell animal. What do? They penetrate, they disrupt and break the cell membrane, which kills the cell. All right? You bust open that cell membrane, and all of a sudden anything can go in and come out, and you have killed the cell. But they're designed not to attack eukaryotic cell membranes of multi-celled animals. And that's why your gut loses all of its bacteria when you take antibiotics. It kills all the bacteria in your gut, and you have to take probiotics to restore the bacteria that your digestive system actually depends upon. Okay, any questions? That's chapter 17. Now, in about 35 minutes, I need to cover half of chapter 18.
Let's get cracking.
Okay.